Welcome to Quantum Mechanics for everyone. Today we're going to be talking about Penneys game, When Fair Isn't. So this is a game that involves flipping coins. Penneys game was invented by Walter Penny. It's a game that appears to be fair, and even under close scrutiny it really looks fair, but it turns out to be anything but so. Understanding why this is the case is difficult, so we're going to take it in steps. Suppose you bet with a friend whether the next flip of a coin will be heads or tails. Now there are two possibilities that are going to occur. It'll either be heads or it'll be tails. There's a 50% chance that you'll win with heads and a 50% chance that your friend wins with tails if the coin is fair. And that exhausts all possibilities. And so this is a fair game. Suppose instead you change the game and you pick the option of two heads in a row, and your friend picks the options of heads followed by tails. Now, we know by just looking at the probabilities when two coins are flipped that there's a 25% chance for heads to come up, and there's a 25% chance for heads tails to come up. So it seems like this game is also completely fair, just like the case with single heads. And each person should win half of the time. So you go ahead and you play the game, and you rapidly discover that your friend consistently wins more than you. Why is this the case? Well, let's take a look at the probability of flipping heads followed by tails. The probability to flip a particular sequence of coins turns out to be complicated to work out. In principle, we can use our general formula, which says how many successful tries are there versus how many tries are there. But the problem is, we don't know exactly how many coin flips we're going to have to do before we have to stop. Because we could get heads tails on the first try, or we could get tails tails, then heads tails, or we can get tails heads heads, heads tails, and so forth. And the total number of coin flips is changing each time before we end because we've found the HT pattern emerging. So this problem and this type of problem often arises in the theory of probability, and there's well worked out techniques that you use to solve it. I simply don't have the time to derive for you what the formula is for how we proceed, but I hope you will view the answer that I give you as being very reasonable. And the question is, how many times do you have to flip a coin on average to get a heads? The answer is, if the probability to flip an H is Q, then the number of flips on average is 1 over Q. And so for our coin, where Q is equal to a half, because it's a fair coin, we find on average we have to flip 2 times to get a heads. And that should be pretty reasonable. On the first flip, I'm either getting a heads or a tails. And if I got tails, then on the second flip, I have a chance of a half of getting heads or tails, and so forth. And it turns out that this actually ends up being a geometric series that you can just sum. And you will find that on average it'll take 2 flips to get heads as the answer for a single coin. Okay, so that's good. So we need to flip then 4 times to get heads tails. 2 times to get the first heads, and then if I keep getting heads, once I get tails, I will stop, and on average it'll take me 2 more flips to get tails. Okay? So we can think of it in terms of the enumeration as saying that we've already achieved heads, and half the time we'll get heads heads, and half the time we'll get heads tails. And for the second case, we stop because we achieved our goal. But if we've got heads heads, then half the time on the next flip it'll be heads heads heads, and half the time it'll be heads heads tails. The second one achieves our goal and we stop. But if we rolled the first, we have to keep going on. And so you can immediately see that the average number of extra flips will be a half of the time it takes 1 flip. That's when I flip heads tails. A quarter of the time it'll require 2 flips. That's when I get heads heads tails. An eighth of the time it'll take 3 flips. That's when I have heads 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 tails, and so forth. And so I get this series that is very similar to the geometric series but different. It's the sum n equals 1 to infinity of n times a half raised to the nth power. Now, I haven't told you exactly how you can sum such a series. It actually is easiest to do if you know a little bit about calculus, and those of you who know calculus might want to try to figure out how you do it. The answer is 1/2 times 1 over 1 minus 1/2 quantity squared, and if I evaluate that, the denominator becomes 1/2 squared, which is 1/4, but it's 1 over 1/4, so that becomes 4, and then I have the leading factor of a half, so the net result is 2. So it turns out it'll take me 2 more flips to get tails, and so it becomes a total of 2 plus 2, or 4 flips to get heads tails on average. Okay, that number seems very reasonable. 2 flips to get heads, 2 flips to get tails. And so your question would be, well, shouldn't that be the same in the case for heads heads? And here's where the rub is. It turns out that it isn't. It's more difficult to calculate this case. In the previous case, once we flipped an H, we basically then just had to wait until we flip a tails again and we're done. But for this case, if we flipped an H and then we flip a T, we have to wait to get an H again before we can get 2 H's. So in essence, we have to start the whole process over again. And so if we will let n denote the number of flips that it will take on average to get HH, we can compute n as follows. N is equal to 2 plus 1/2 times 1 plus 1/2 times n plus 1. Now let's see if we can understand where each of those different terms occur. And notice there's an n on both sides, so we're going to ultimately get an equation for n that we have to solve. Well, n is the number of flips on average to get HH, so that's the number that's going to be on the left-hand side. How do I determine what it is? Well, it takes 2 flips on average to get the first H, and then half of the time it takes 1 more flip to get the second H. And then we're done. So that determines what happens half of the time. Otherwise, I did 1 more flip and I got tails. So half of the time I did 1 more flip and now I start all over again. So it's going to take n flips to get the answer. So with probability a half, I have to multiply by n plus 1 because it took that 1 extra flip to get tails. Now that's a self-consistent equation that we can solve to determine n. And you see that you get n equals 3 plus 1/2 n. And so if you then solve for n, you find n is equal to 6. That's bigger than 4. So it actually takes longer to get heads heads. It takes more flips on average to get heads heads than it does to get heads tails. And this is why you're going to lose in this game. It seems to me, when I look at this, to be magic, but the key is that for the heads heads choice, when you nearly get it but don't, you have to restart from the beginning. You lose that first heads that you had. Whereas for heads tails, if you don't get it on a particular flip after heads has appeared, you just wait because eventually you'll get it. You don't have to restart from the beginning again. So Penny's game takes this idea one step further. In his game, it turns out there's a strategy that guarantees you'll win regardless of what the other player picks. If I tried to do this with the 2-flip game, if you pick heads heads, I pick heads tails, or I pick tails heads, and I'm going to win more often than you are. If you pick tails tails, I will pick heads tails, and I will win more often than you. If you pick tails heads, I'm going to pick heads tails, and we each have an even chance to win. That's sort of a 50-50 chance. But it turns out when you go to 3, a pattern of 3 in a row, there's a strategy that allows you to always pick a winner. Okay, so let's take a look at Penny's game. We're going to give that complete winning strategy for you on the web page after the video. What I'm going to do for you here now is I'm going to evaluate the case if player 1 chose heads, 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 which is a particularly poor choice to make. And then the optimal choice for player 2 is tails, heads, heads, and you'll see why that's the optimal choice in just a moment. Okay, in this case, player 2 is going to win 7 out of 8 times, which is kind of a shocking number. So you might ask why. Well, let's try and see if we can analyze it. The idea is we have to first look at what are the 8 possible first flips of 3 coins. They're heads, 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 tails, heads, tail, heads, heads, tail, tails, tail, heads, heads, tail, heads, tails, tail, tail, heads, and tails, tails, tails. Okay. Of those 8 choices, if player 1 flips heads, heads, heads on the first time, he's going to win. He got his pattern. Okay, that's going to occur 1 out of 8 times on average. The thing that's so shocking is if any other result occurs, then player 2 is going to win. How, you might ask? Well, now think about this. Before you start flipping heads for anything further down the chain, the last coin before your first heads has to be a tails. So if you flip tails, heads, 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 you might think player 1 wins. But look carefully. Before the heads, heads, heads appears, there's a tails, heads, heads. So player 2 won because it occurred before heads, heads, heads. And it turns out this is always the case for all 7 out of the 8 other options. So then this analysis shows you how you can find a winning strategy that will be very successful for one choice of player 1. Now, player 1 has a total of 8 different choices. It turns out that the worst that you'll ever have if you pick your winning strategy is that you'll win 2 out of 3 times. There is no choice that player 1 can make that will win. And yet, the game seems like it should be completely fair. Even after this analysis, to me, when I think of it just on the spot, it seems like the game should be completely fair. So you're going to have the opportunity to explore this a little bit more in the problems. And I just want to caution you that those problems are really quite hard. If you can't solve all of them, please don't worry. Those are the hardest problems I'm giving you in the entire class. And if you don't get them right, you don't. But I figured it would be a good idea to give some challenges because there are probably some of you out there who will be able to figure out how to do it. And with that, we're going to finish. This has been Quantum Mechanics for Everyone.